guys, so today we're going to be looking at chapter 4, section 2, adding, subtracting, and multiplying polynomials, part 2. So we're going to start off here with multiplying a 3 binomial. So for example, let's say right here, we're asked to multiply b plus 4 to the power of 3. Now if you remember, I said that before, if you have parentheses where you have two terms inside and they are adding with each other, you cannot distribute the 3 to both terms. It's not possible. The reason why is because if I were to expand ab plus 4 to the power of 3, we would get here, let's see, ab plus 4 to the power of 3, we would get here ab plus 4 times ab plus 4 times ab plus 4. And when you multiply all three together, you're not going to get the same thing as if you were to distribute the 3 exponent with the 4 and the ab. So just a reminder, whenever you have an addition sign or a subtraction sign in between the terms, you cannot just distribute the 3 to both terms. That's not possible. Okay. So I'm going to multiply all 3 terms together. I'm going to use the foiling method. Start off with these 2 factors. So multiply ab with ab, multiply ab times 4, and then afterwards I'll multiply 4 with ab, and then I will multiply 4 with 4. And I'll leave the ab plus 4 alone on its own. So right here, if I have here ab times ab, I'm going to figure out that equals 2. I'm also going to multiply ab times 4. On the other side, I'm going to multiply 4 times ab and 4 times 4. Okay. So ab times ab, that equals to a to the power 2 times b to the power 2. ab times 4 is 4ab. Then 4 times ab is just 4ab. 4 times 4, that just equals to 16. So we get our new expression. I'm going to combine our like terms, 4ab and the other 4ab. So we get here a to the power 2 times b to the power 2 plus 4ab plus another 4ab plus 16. And since we have 2 like terms we can combine, we get here a to the power 2 times b to the power 2 plus 8ab. Drop down that plus 16. And that would be my final answer for at least this portion. Okay? Oops, sorry, not black. There you go. For at least that portion. Let's go to multiplying this entire expression, a to the power 2 times b to the power 2 plus 8ab plus 16. And we're going to multiply this with, let me move it to the side, with the last ab plus 4. Okay. So now I'm going to multiply those two together. I'll leave it right here. I'm going to move this to the side over here. So again, we only multiplied these two together, so I need to multiply my answer from this 2 with the last ab plus 4. So when I do that, again, I'm still going to factor. I'm going to multiply ab with a to the power 2 and b to the power 2. I'm going to multiply ab with 8ab. The last one I'm going to multiply it with is the 16. Okay. So right here, if I do that, ab times a to the power of 2 times b to the power of 2. I'm also multiplying ab times 8ab. ab is going to multiply with 16 as well. And then for the other I'm going to distribute 4 to a to the power of 2 and b to the power of 2. I'm going to distribute it with the 8ab. And the last one is to the 16. So when I do that, I have here 4 times a to the power 2 times b to the power 2. 4 times 8ab and 4 times 16. So ab times a to the power 2 times b to the power 2 is just a to the power 3 times b to the power 3. For the other one, I have here 8a to the power 2 and b to the power 2. 16 times ab is just 16ab. On the right side, we get here 4a to the power 2 times b to the power 2. This becomes 32ab. And the last one is just 64 on its own. Okay. So I want to still combine any like terms. I see here the like term for a to the power 2 and b to the power 2. And I know that the like term for 16ab is 32ab. So if I were to multiply it, I get here a to the power 3 times b to the power 3 plus 8a to the power 2 plus b to the power 2 plus 4a to the power 2 plus b to the power times b to the power 2. And then I also have here 16ab plus 32ab plus 64. So when I combine the like terms together, I get a to the power 3 times b to the power 3. This becomes positive 12a squared b squared. Then I get here positive 48ab, and I just drop down the 64. And that would be your final answer after multiplying all three. Now, doing this consistently is going to take a lot of time. And so, rather than having to go through multiplying all three terms and foiling every single one of them, there are a few special patterns that we can discuss. So, three of them would be the sum and difference formula, where right here, if you know that the two terms are the same with each other, and one of them is adding and the other one is subtracting, you know that the formula here would be a to the power 2 minus b to the power of 2. So, for example, right here we have x plus 3 and x minus 3. This aligns with our a plus b and a minus b format. And from here, I can determine that a would have been equal to x and b would have been equal to 3. So if that's a case where it does align with the a plus b and a minus b format, I can use the other part of the equation, a squared minus b squared, and substitute my terms for a and b. So we get here a is equal to x and b is equal to 3. We get here x squared minus 9 as my final answer. Another type of special pattern, product pattern, is the following, where if you have two factors that are both the same term and they're being squared, then we can use the formula a to the power 2 plus 2ab plus b to the power of 2. If they are negative, the important part here is to note that the only part that's changing is the negative sign with that 2ab. Everything else just stays the same. So let's say that, for example, we were asked to find out what the product of 2t minus 5 to the power of 2 would equal to. So first I need to find out what my a value is and what my b value is. So from the formula a minus b squared, I know that my a is equal to 2t and my b is equal to positive 5. Now if you notice, this was a negative 5, but I made it positive. The reason being is because I'm already taking that negative sign from my formula. So I'm still just left with the 5 and the 2t being a. So right here, from my formula, we get the equation a to the power of 2 minus 2ab plus b to the power of 2. And when I use that second part of the equation, I just have to substitute my a value and b value into the equation. So I get here 2t squared minus 2 times 2t times 5 plus 5 to the power of 2. So after I do that, I just have to simplify my expression. Now in this case, because the 2, let me just enhance it for a moment. Because right here, we see that 2 is multiplying with t. Then, in this case, yes, it is okay to distribute the 2 to both the 2 and to the t. The only time you cannot distribute an exponent to or anything inside the parentheses is if, for example, there was an addition sign in there or a subtraction sign. In these cases, you cannot distribute the 2 to both the terms 2 and t, basically. But whenever you do have multiplication, that's fine. You don't have to worry about not having to distribute the exponential power. So if I distribute it, I get here 2 to the power of 2, t to the power of 2. This becomes negative 2 times 5, which is negative 20 t, and this becomes 25. So we get here 4t squared minus 20t plus 25 as my final answer. Okay. On the other side, we have the last one, which is cube of a binomial. So if we have cube of a binomial, and let's say you have a plus b and it's cubing it, just kind of like how we did over here on this problem. Right here, we had a cube situation, right? Still doing the same thing here. Just making a shorter way. Yeah, shorter way of solving for it. So if I have, for example, here z plus 3 to the power 3, then I'm going to take the formula, not this one because it has a negative sign, but the top one instead, where we have a plus b is to the power of 3. Our a value equals to z, and our b value equals to positive 3. Okay, so if I'm plugging it into this equation here, I have here the expression a to the power 3 plus 3a squared times b plus 3ab squared plus b to the power 3. Then I substitute it in. I get here z to the power 3 plus 3 times z to the power 2 times b, which is 3, plus 3 times z times 3 to the power 2 plus 3 to the power of 3. And then I'm just solving for it. So z to the power 3, this becomes 3z to the power 2. Actually, it doesn't, because right here, I still have 3 times 3. So that turns into 9z to the power 2. This becomes 3 times 3 is 9, times another 3 is 27, so 27z. And 3 times 3 times 3, that just equals to positive 27. So that would be my final answer. Okay, and that's a lot shorter than multiplying 3 of the same terms with each other. That takes up way less time. Okay, so another type of product pattern or special pattern for multiplying binomials is Pascal's triangle. Pascal's triangle is a special pattern only when the two terms are adding with each other and you have an exponent on the outside. Now remember, this is when they are adding. It can use subtracting, but there's going to be a little trick, which I will show later on in the example. So, whenever you're looking at Pascal's triangle, which is on the left side here, the idea here is that for Pascal's triangle, you always start off with 1 first. And then from 1, you get another 2 ones. Now from here, I want to add up my 1's together. And when I do that, 1 plus 1 equals to 2. And every single time I insert another row, I also have to insert another 2 1's on the side. So when I do that, 1 plus 2, that equals to 3. Over here, 1 plus 2 equals to 3. Then again, inserting another row of 1's. And then from here, we keep on going with that pattern. 1 plus 3 equals to 4. 3 plus 3 equals to 6. 3 plus 1 equals to 4. And again, 1's are on the outside of this. And then, so I just went to the 5th row so far. And so right here, 4 plus 6 equals to 10. 6 plus 4 equals to 10. 4 plus 1 equals to 5, and 1 is on the outside. Now, the reason why we want to know the Pascal's triangle is because when I am multiplying a binomial, you're going to notice that we use this pattern. So, a plus b to the power of 0, that would be our first row right here, where we just get 1 as our answer. Then for our second row, we have here a plus b to the power of 1. So in that case, we have 1 and 1 down here. And so same thing, we get 1 and 1. And I'm just adding a plus b because it's a plus b to the power of 1, which means that that's just basically a plus b. Okay. Second row we have here is a plus b to the power of 2. So from a Pascal's triangle, I'm using the numbers 1, 2, and 1. So I have here 1, 2, and 1. And I'm always going to start off first with a being the highest exponential power that's provided here. So start off with a to the power of 2. And I'm slowly going to decrease the exponential power every single term that I get. So I get here a to the power of 2. This becomes a to the power of 1. And this one, you see that we just don't even have an a. And while the a values for the exponential power are decreasing, I'm going to be increasing my b values. So over here, there is no b. Then we get b to the power of 1, and then we have b to the power of 2. We stop there because, again, our exponent was originally to the power of 2. I'm going to keep on doing this. So right here, a plus b to the power of 3. I'm going to look at the Pascal's triangle so I know what my coefficients are. My coefficients are going to be 1, 3, 3, 1, which is shown here. 1, 3, 3, and 1. And then, to find out what my variable is, I'm going to start off with the largest one, which is a to the power of 3 here, because we know that the exponent is to the power of 3. Then we're going to just keep on decreasing it. A to the power of 2, then a, and then nothing for the last term. And then for b, we start off with nothing. Then we get b to the power of 1, then b to the power of 2, and then the last one is b to the power of 3. So let's say if we have here a plus b to the power of 5. My coefficients end up being 1, 5, 10, 10, 5, and 1. And I'm going to start off with a being to the power of 5. And one by one, I'm just going to get smaller and smaller. A to the power of 4, a to the power of 3, then a to the power of 2, a to the power of 1, and then lastly, no a. And then for b, starting off with just no b, then b to the power of 1, b to the power of 2, b to the power of 3, b to the power of 4, and b to the power of 5. Okay? So it's pretty useful to know the Pascal's triangle because of the fact that, let's say you have here x minus 2 is to the power of 5. I don't really want to multiply x to the power of 5, 1, 2, 3, 4, and 5 times. That would take forever. So understanding the Pascal's triangle makes your life so much easier. So if I have the power of 5, right? I'm going to look at the column, or the row, where we have power of 5. So this was for row 0, 1, 2, 3, 4. This is for row 5. So for row 5 here, my coefficients are going to be, 1, 5, 10, 10, 5, and 1. So I'll start off with writing that out first. We get here 1, 5, 10, 10, 5, and 1. And again, because we have to the power of 5, that means that my a value, which in this case would be x, is going to be this first term, and it's going to be to the power of 5, okay? And I know from here that this is going to have to get smaller and smaller and smaller. X to the power of 3, x to the power of 2, then x to the power of 1, and the last term is just going to have no x, right? Then the second one that we have here is our b value, and our b value is going to be -2. So this part is where it gets a little tricky. So originally in the other ones, I said that we keep our signs separate from each other over here, right? Where I said that even though it's negative, I'm going to make sure that I keep my b value positive. But in the Pascal's triangle, my a value is going to be x, and my b value is going to continue to be -2. Okay? So, right here, I'm not going to put anything over here for the first one. That's going to be just empty. But for the second one, I have here -2 to the power of 1. Then I have here -2 to the power of 2, -2 to the power of 3, -2 to the power of 4, and then the last one is going to be -2 to the power of 5. Now between each term, I'm just going to add addition signs in there. Okay. So when I solve for it, I get here x to the power of 5 plus, this becomes -10 x to the power of 4. This becomes positive 40 x to the power of 3. We get here -80 x to the power of 2. We get over here 80x. Then the last one here is -32. So right here, the only one that I really need to change is this one right here. And I think that was it. So right here, that just becomes x to the power of 5 minus 10 x to the power of 4 plus 40 x to the power of 3 minus 80 x to the power of 2 plus 80x minus 32. And that would be my final answer. So hopefully this helped. Good luck.